Hello, everyone. My name is Leon Crisp, and I am going to be talking today about contract-based programming. So let me just share my screen and we can get started. Right, here we go. So I'm going to be giving you an introduction to the power of contract-based programming, and let's have a look at what we're going to be talking about. So today, you're going to learn about what contract-based programming is. Then we're going to have a look at what a contract contains, and then how to implement contract and use it. We're going to look at some examples, both of templates and actual code, actual use using contracts, what a contract may look like in real life. Rounding off with some best practice for contract-based programming, about how to use it, and ultimately how it leads to more productive and enjoyable software development. That's where we want to get to. There are a few other names you may or may not have heard of for contract-based programming. There's by contract programming, programming by contract, design by contract, code contracts. They're generally pretty much the same thing. And most of these are really focusing more on the automated testing that a contract is adhered to, so defining that within the code itself. I'm going to be talking about a bit wider scope than that because there are quite a lot of focus on the documentation side outside of that as well, which I think is important. So about this talk, I'm going to be focusing on an object-oriented environment. Obviously, you could use code contracts outside of that. And I'm going to be focusing on methods mainly. You can create contracts against whole classes, but we're just going to focus on methods for now. I use Salesforce examples where possible. And I'm going to be taking a slightly different approach than the by the book approach. As I said, a bit wider scope. I've taken various things from various places and added some of my own parts. So hopefully it's going to give you a good initial understanding and starting point that you can take and adjust your own preferences with some actual usable templates and so on. My slides are fairly detailed. The reason being this is a recorded talk, and so you could stop any time and have a look at the details, or when you go back over the recording, so it's there to make it as useful as possible for you, but I will be skipping over some parts. I'm going to start with what contract-based programming is, then look at the how, and only finally get onto the why, because I think that once you know what it is and how it works, it's going to make a much more sense of why we're going to why we'd want to do that. And so I'm not going to be doing the typical start with why approach. First question, then what is contract-based programming? We're going to have a look at the what, and in a nutshell, it's all about defining the exact functionality of each method, and then ideally checking and testing it that it's not broken. And by functionality, we mean from a black box perspective, not anything internal to a method, but the outside world black box functionality. So this then defines the contract. The functionality defines the contract of how the method will behave, how it will interact with the outside world. The contract should never be broken, and tests can be put in place to detect if that happens. Where possible, you want the method to automatically detect if the contract's broken and explicitly fail. You can't always detect every type of contractual conditions, but many of them we can, and we can put automation to detect that, which we'll have a look at. And in which case you can inform the developer or the unit test or the calling code of that failure, usually by raising the exception. Continuing with the question of what is contract-based programming. So if a contract is ever broken, that means there's a bug in the software. That's one of the really valuable things about contracts. And it means either the calling code or the method itself has a bug. Runtime errors are different, as we'll see later. If there's a runtime error that throws an exception, that doesn't mean the contract's broken. It doesn't mean the method is broken. This is just something that's expected to happen in certain circumstances. However, it may still be part of a contract to raise a certain type of exception or handle an error in a certain way. So still may want to define, or most certainly will want to define, the error handling as part of your contract, because that's part of how it interacts with the outside world and part of the defined behavior. So by contract approach, which is one of these sort of flavors of programming by contract, asks, when is it appropriate to call a method? That's your precondition. What is the method supposed to have done? That's your postcondition. And did the method execution mess up the state of an object? That's your class invariance. And we'll have a closer look at all of those actually. And your contract for a method acts as the primary documentation for the behavior of the method. It's a point of use documentation because you put that documentation right at or within the method, which is the best place to have the documentation. So now we need to ask this question: what defines the functionality of a method? Because the answer to this is the answer to what we put in a contract. Well, let's start off by having a look at a diagram. This is a really great diagram, which I've taken from Wikipedia, and it really shows you pretty much everything that goes in a contract in terms of the high level. So in this diagram, the yellow part represents your method. Then you have inputs to your method of various types, and then outputs. And actually, side effect, you have side effects, which are really a type of output, a special type. So, and then your method can raise exceptions and errors. So let's have a just go through these. So there are two places really that you want to check your contract conditions are met. These are preconditions. You need to check that before the method runs and can run successfully, certain conditions need to be true. These are generally about input values. And those input values could be parameters, they could be class properties or state. But unless these preconditions are met, the method can't guarantee to give the right results. So this is part of your contract, and it for the calling code to make sure the preconditions are correct. Then post conditions are at the end of executing the logic of the method. Then certain conditions must be met contractually. It must in effect be give the right output, the correct output, and also it must give the right side effects. So the difference between output values and side effects is output values are, say, your return values, and also your parameters that are passed in, which are in-out parameters. In effect, they may be passed by reference or an in-out parameter that's going to be that can be passed out. In effect, can be changed and come out the other side. Whereas side effects are other changes to things that aren't specifically passed in or on return values. So these could be your class properties, for example, that you update, but still it's a kind of output. And your post condition is to make sure these are all correct contractually. So let's have a closer look at these. I'm going to start off by just a reminder of the scope of influence of a method in OOP. What can a method act on or change in OOP? And the reason for having this reminder and asking this question is this is core to defining the functionality and therefore the contract of a method. We need to know what can the method actually change. And I'm not going to go through this in detail. I'm just showing this as a for you to refer to. So there are the four things really a method can act on, and you can come back and look at this. It's just a reminder. So in terms of defining the functionality of a method, we're interested in the interface in the wider sense, meaning how this method interacts with the outside world. That's its interface in the wider sense. Outside world being outside of the black box. So we have inputs, exceptions and error handling, outputs, and side effects, as per the diagram we were just looking at. These are the ways method actually interacts with and changes the outside world. And therefore, these are all elements of contract, elements of the functionality, the defined functionality of a method, the specification of a method, in effect, and therefore the contract. Inputs are your parameters, but also the state and properties of the the method's class, method's own class, but it could be of parent classes or component owned or reference classes. Exceptions we'll have a closer look at in a minute, and outputs, as I say, these are the return values or parameter changes, and then your side effects are your changes apart from what's called outputs, which are your state changes, basically changes to this type of input. Right, so there's one more thing called invariants, which wasn't shown on the diagram, and these, in effect, not something different than these, but they're a special sort of class of related to these things here. So invariants are, well, I'm just going to go to the next slide where we dive into what invariants are. So invariants are statements that must always be true and invariably be true. And that's why they're called invariants, because they're invariably true, always true. And these therefore need to be true at both method entry and exit. And for a class invariant, they're true for the whole life of the class or instance. So that's why you have class or object invariants, and you can have an invariant that's scope is just a method itself. Often they're actually class invariants, and we'll have a look at those. So at the precondition stage, the invariant statement must be true, and at the postcondition stage, it must be true, and actually the whole way through the method, really. If the method temporarily breaks the invariant, as in the invariant statement becomes untrue somewhere within the method, it has to be corrected before exiting the method. That's what's important as part of the contract for invariants. So some examples here. Day and hour are two examples of invariants. They could both be a class invariance. Day could be a class property. And throughout the whole method, day should always be between 1 and 31. Hour should always be between 0 and 23, both at point of entry and exit. Let's have a look at exceptions, just to drill into that a bit, because we want to categorize exceptions just for our purposes of our contract. So first of all, we have type of exceptions that are indicating a programming error of the caller if they're thrown. These should never happen, obviously, because we don't want any programming errors, so they should never fail. Next, we have a type of exception that indicates a programming error in the method itself. Again, we don't want these to ever happen, but if they do, that's what they mean. And the third type is an exception that's thrown for a normal runtime error, and we specifically need to differentiate between these programming error exceptions. These are exceptions indicating the situations occurred that we expect to occur in time to time, and it can be a design decision that a method will throw an exception in a certain circumstance, and that's not indicating any bug or anything like that. And the other side of the contract are the condition elements. So these are preconditions and postconditions, as we saw from the diagram. So how these relate to what we've just been looking at, I'll just put them underneath there. So precondition are basically your inputs, and your postconditions are basically your outputs and side effects that they apply to. So the preconditions apply conditions against inputs, and the postconditions apply conditions against your outputs and side effects. For example, allowable values, allowable ranges of values, and so on. The other one to add here is invariance. As I said, that wasn't on the diagram, but that's a contractual condition that has to be true both in the pre-condition stage and the post-condition stage. Same condition applies with both. So coming back to our diagram here, hopefully this makes a bit more sense. As I said, it's a great diagram to refer to. It's only invariants that don't show on there, but an invariant is a type of condition which spans both the precondition and the postcondition, and in between, really. Another aspect of contracts want to point out, there are two main sides of contracts. You have the documentation side and your encode checks. So just focusing on the documentation to start with, the documentation provides your functional specification, in effect, your contract for the usage of the method. And this is really valuable because by defining exactly what it does, what it should do, you can actually test properly that it does do what it should do. So it's used to test against in unit tests. The unit test can make sure that contract's fully met. Also, developers can use it to know how to correctly use a method, and also developers can use it to know if they're making any changes to the method to make sure their changes stay within contract. And then encode checks are the automated checking that a contract's not broken, which are actually really helpful to know straight away automatically if a contract's been broken. You can't necessarily check every contractual condition. Some of those might end up being just in the documentation because you can't easily check it in code. But where we can check it in code, it's great to do that. And these checks could be done at compile time, potentially. Even pre-compile time, there could be static checks done. They can be done in unit tests, again, as mentioned here. But the unit tests could trigger these code checks, and therefore the unit test knows there's a failure. And it could be runtime checks, actually while it's running normally in production. Let's have a look at what's in a method contract document. So looking at the documentation side, there's a lot on this screen. It's just to show you all the types of things that could be there. Again, you can take it, what you want from this. First of all, we have things like who it was created by, method name, purpose, description, the scenarios handled with examples ideally. Then we go on to the more kind of technical parts, the parameters, the return values, and the outputs, other outputs apart from return values, and the side effects. So those are all your kind of in-out stuff. And then you have your contractual conditions, which are your preconditions, your post-conditions, and your invariants. They can and should all be documented. Also, it's discussed your exceptions and error handling should be documented as to how that's going to work, at least in terms of what's visible to the outside, any exceptions raised, and so on. That's part of the specification of the contract, of the method. You may want to include acceptable performance criteria because it may be important to the method that it performs within certain criteria, and that could be part of the contract, part of the specification. For example, time taken or amount of resource used. And also, you may want to document associations, dependencies, if any, and just placeholder for any other information. So let's have a look at how that might actually be implemented. Here is a template which you can take and use and adjust how you like, that you could use to document your methods. So as you can see, it has these app tags to and structured sort of fields after that in effect to put the information. So this structure allows it to be machine interpreted in effect. You can create automation to create documentation from this in different formats, for example, to extract and document. You can do automated checks from this. You could do static checks to make sure parts of the documentation are in place, or even potentially check some of the conditions in the document. You could potentially even take some of these parts and automatically create code from them. But at minimum, you just want to document it in a standard format for each method. This could go at the header of your method, as in outside your method, just at the top of it. Or optionally, you could put some of these elements in your method. You wouldn't necessarily want to put these top things in there because these are who created it, description, scenario examples, but your documentation against your parameters and so on, and your preconditions, returns that you could, if you want to, put those where they happen in the code, and you can create something, documentation software, to pull that all out and put it in a nice format if you wanted as well. So let's see how this could look in use, just with an example here. So I've created an example using a method name, a method called deposit. So imagine there is a class called bank account. It has various methods on it, like deposit, withdraw, open, close, and so on. So this method is a deposit method of a bank account class, and so we have a description here. It's going to provide deposit amount as a deposit amount to the bank account, and so on. We have scenario example. Documented the parameters, what it returns, a side effect here, which it's going to update the balance property of the class. So this isn't a parameter passed in, but it's going to update that, so that counts as a side effect. We have an invariant here because actually the bank account class, we have several invariants. We have a look at that, and we're saying all bank account class invariants apply here because if there were any method specific invariants, we could add them here, but for now we're just saying that. Post condition, the balance on entry must have balance on entry as a device must have increased by the time you exit, because you're adding some amount to it. And an exception, we're going to add an exception as to show an example of a runtime exception, that you can't deposit if the account is closed. You can only deposit into an open account. No performance conditions, no other notes. So that's the documentation side in an example. Now we have a look at the encode tests. Sometimes these are called annotations. So the types of tests we have are actually 4 types. We have precondition tests, as we've been looking at preconditions already, but these tests are sometimes called requires or expect, because your method requires these conditions are met or expects these conditions to be met. They must be guaranteed by the calling code that they're met. If these encode tests fail, then it means there's a bug in the calling code. Then you have your post condition automated checks. These are sometimes called ensures or guarantee, because your method is ensuring or guaranteeing that these conditions are met, these contract conditions are met. If these tests fail, it means there's a bug in the method itself. Then you have an invariant check, sometimes called a maintain, because the condition must be maintained as true throughout the whole time. So where the bug lies depends where this happens, because obviously an invariant, as mentioned, has to be checked both at the precondition stage and the post-condition stage. So if the invariant check failed on entry to the method, then it means there's a bug in the calling code, or it could be in the class, somewhere else in the class. If the invariant check fails on the exit of the method where we check post conditions, then that means the method itself has a bug in it, because it didn't maintain that invariant being true. It must have been true to start with, else the method wouldn't have run. It would have failed on entry when it did its invariant check at the start, and so in that case that means there's a bug in the method itself. Finally, we just have a bit of a catch-all here for another type of contractual encode test for when it's not one of these 3. If we want to check any other contract conditions, we can just use an assert contract test. And again, if that fails, it means there's a bug in the method itself. Let's see how we can implement this now in Salesforce. Apex. Here's an example of how we could implement these encode checks. I did a class here called code contract. It's a global class, and this has 4 methods in it, which are 4 types of test. For these 4 types we've seen below, we have a requires test, an ensures, an invariant, and an assert test. And each of these throws a different type of exception: a requires exception, ensures exception, invariant exception, and assert exception. So we know what type of contract failure has happened. So let's have a look at how one of them is structured. We'll look at the requires. Basically, you pass in a condition and a string. So the condition is the one to check if it's true, and the string is what is going to be the one used in your exception raised, which basically describes the contract condition that will have failed if this exception is raised. So if the condition is not true, if it's not met, it's going to raise the relevant exception, passing that message. So in this case, it's going to say contract required failed, and add your message to the end of it like that. So same approach for the others. So we can have a look at how we actually use that now. And this kind of brings together all the elements we've been talking about. So this is again a bank account class. I've omitted most of the code here. All the other methods and so on aren't shown here, just the deposit method and a private method to check the class invariants. So let's have a look at first at this check class invariants method. Because the class invariants should be true, they must be maintained, must be true throughout the life of the class, and therefore every method, they should be true at the start and the end, and actually throughout the life of every method. We don't want to keep redoing these checks all over the place, so we create one method here, private method, to check all the class invariants. We just put 2 here, but you might usually have a number more for a class. So we're going to check that the balance is always greater than or equal to 0, because for this type of bank account we're implementing, it can never have a negative balance. So balance must be greater than or equal to 0, and the account number should never be null, because when you actually create an instance, it should have an account number from the start, and so we have another invariant check there. So we're going to call that from within our method at the appropriate points. Right, our method here is called deposit, and that takes in a deposit amount, which we're going to add to the balance of the account, and it returns a decimal, which the documentation that we looked at before it explains is the new balance after the deposit. So we divided the method into 3 sections that has a comment at the head of each, and this is a recommended practice for every method actually, particularly when you're using code contracts, but it's sensible anyway. First section is your precondition checks and initialization. Then you have your main logic, and then you have your postcondition checks and your return if you have a return balance. So let's have a look at those 3 sections. Precondition checks and initializing. So what we're doing here is all our code contract requires checks we put here. So in this case, we just have one example: deposit amount greater than 0. The parameter passed in, it should be greater than 0. Otherwise, there's an error in the calling code, and the contract's been broken. Or bug in the calling code, I should say, rather than an error. Then we check our class invariants, because they part of your precondition checks as well. So we call this check down here. Also initialization, we're just grabbing a starting balance value because we're going to check that in the post condition. Right, now getting onto the main logic, and this should always be in a try finally block, with the invariants check in the finally block, because invariants have to always be checked before exit, whether you've exited successfully in returning a return value, or whether you've exited through a failure and an exception being thrown and jumping out. You should always check that you haven't violated the contract of your class invariants, and so that's in a finally. So within this logic here, we have the another check. This is a runtime check to show you differentiating from the contract checks. This is checking if the account's closed. If it is closed, it throws an exception, can't deposit to a closed account. It's going to jump out here, run your finally check to collect the class invariants, which is your only exit condition in this case. And the calling code, well, it can do what it likes with that, but that's a defined piece of functionality that in that case it will throw that exception, so your calling code should know what to do with that. Then we update, if that's fine, we update the balance, which is the only thing we do here. Again, whether successful or not here, whether we throw an exception or not, we're going to check these class invariants. Then we come to the post condition checks. Again, here's where you would have all your code contract ensures checks. In this case, we're just checking that the ending balance is greater than the starting balance. It must have always increased after a deposit. And then we're going to return a return value. So that's it, basically. I'm now going to look at best practices, quick run through those. So make contracts explicit, structured, and machine discoverable. As we said, this is so we can do automated code checking, static checking, and particularly document generation. So we can, through that machine discoverability, we can automate things. Use runtime checking of contracts, as we're just looking at, so we automatically detect any contract breakage, or at least all the ones we can automate. Runtime contract checks check programmer errors. So not runtime errors, so differentiate between those. Contract checks are only for programmer errors. And unit tests should test and reflect the contract. The idea is to test the whole contract as much as possible. Have only one exit method for the reasons I just explained. And with runtime checks, you may want to, the runtime contract checks, you may want to enable them only in debug mode if you're concerned about performance. This is an option, just a consideration, because you may not want them running in production. Another option is to make them a soft error in production if you just don't want the methods failing, so it doesn't fail the method, but it just says logs an error. Now we get on to why. As I said, we'll look at why in the end. We're putting a table here together without contract-based programming and with, so you can have a look at that. I'll just quickly run through. So without contract code method contracts, you haven't, a method is not defined in terms of functionality, in terms of what it should do. So you can't create effective unit tests to test it does what it should do if you haven't defined what it should do. In effect, you end up testing it does what it does, which isn't very effective. And it's even harder for someone to create a unit test for someone else's code, because again, they don't know what it should be doing. So unit tests then easily miss some bugs. So you get more getting through to QA production, code hard to maintain. You end up with fragile code. It's easily broken, and it becomes more fragile over time as these issues accumulate. Particularly as the dev team and code base grows, the quality is really hard to maintain, technical debt accumulates, and ultimately the developer productivity is hindered because it's spending a lot of time trying to work out what each method's supposed to do, how to use it, and accidentally breaking things. With contract-based programming, then it makes a huge difference to all of these things. Your unit tests can confirm it does what it's supposed to, and they can be very accurate. Anyone can create accurate unit tests for someone else's code because it's all specified what it should do, and therefore those unit tests work really well, reliably catch almost all bugs straight away. So the bugs are caught early on, save all that time of bugs being caught later in the cycle and the issues they cause. Therefore, the code's easy to maintain even for new team members because it's all documented and automatically tells them if something's broken. So you end up with robust code that's nearly unbreakable and remains robust over time because your contracts are defined and your contract tests are there, which don't degrade over time. So in terms of scaling up your team and code base, you can do that without quality degradation and without accumulation of technical debt, at least from these sources. And ultimately, your developer productivity is increased and it's easy to use and enhance every method. So in summary, you can catch more bugs, including edge cases. You catch them earlier. You minimize code being broken, both now and in the future. Maximize maintainability of code. Increase effectiveness of the teamwork between developers, and ultimately you increase developer productivity and enjoyment, because if you're productive, it's much more enjoyable and you don't spend time having to sort out all those preventable issues. I'm going to just flash up this page here of further reading. These you can just follow these links. They're all quite useful and interesting articles about contract-based programming or related things. And that is the end of my talk. So thank you very much for joining. So now on to any questions. As this is recorded, I'll pass you to the host now, who's going to gather your questions and pass them to me, and then I will answer them and post them somewhere for you. So again, thank you very much, and bye.